Hello everyone, I am ChryssaThoua. I am an architect and a research student at UCL, Institute of Environmental Design and Engineering. My research project is a collaboration between UCL and Archetype Architects, who are a CIHA project partner. I am going to present a small paper on evidence of in-use performance of two passive house primary schools in the UK in terms of classroom air quality. In this presentation, I will briefly cover the research background and the identified knowledge gaps. I will go through the monitoring methods and a short description of the case study schools and classrooms. I will present results for several monitored parameters, including temperature, relative humidity, carbon dioxide concentration in the classroom, indoor and outdoor nitrogen dioxide, fine particulate matter, and volatile organic compounds. Then I will discuss the practical implications of the findings and finally the next steps in this ongoing research. As part of international climate change mitigation efforts, the UK government has committed a reduction of national carbon emissions by 80% compared to the baseline levels in the next 3 decades. Since schools account for 2% of the national carbon emissions, 15% of public sector emissions, and half the emissions of the local authorities, new schools added to the school building stock need to achieve higher energy efficiency. One way to achieve this is by wider adoption of a stringent energy efficiency standard, such as Passive House. Passive House is an evidence-based certification standard for building energy efficiency that requires highly insulated thermal breach-free and airtight building envelope, with ventilation provisions including systems of mechanical ventilation with heat recovery. At the same time, we need to consider indoor air quality in schools, as the classroom is the second most significant exposure to indoor air pollution after the home. Indoor air pollution can impact health in different ways compared to outdoor air pollution. In addition, it can have an effect on learning performance. Due to mounting evidence on the effects of classroom air pollution on children's health and performance, recent updates of existing guidelines for schools, that is the 2018 Building Bulletin 101, now require a more comprehensive assessment of indoor air quality. This includes monitoring of other pollutants in addition to CO2, which has been used as a proxy measurement for ventilation rates. Evidence gaps limit the industry's ability to benchmark indoor air quality performance of schools and to accurately evaluate the relationship between exposure to indoor air pollution in classrooms and health outcomes. There is limited evidence on indoor air quality performance of UK school buildings, especially lacking comprehensive indoor air pollution assessment. And there is scarce evidence on indoor air quality in passive house schools. The available studies for passive house schools come from countries other than the UK and only included CO2 concentration as a proxy for indoor air quality. This study aims at providing evidence on the indoor air quality performance of UK passive house primary schools and at determining the modifying factors for this school building typology. The method involved continuous monitoring over a school year from October 2018 to July 2019. The monitored variables included temperature, relative humidity, carbon dioxide, CO2, and fine particulate matter, or PM2.5, which includes the ultrafine fractions and fine fractions of PM. Continuous monitoring was combined with passive sampling to determine time-averaged concentrations of nitrogen dioxide, NO2, and targeted and total volatile organic compounds. Targeted VOCs included limonene, which has strong indoor sources and plays a role in formation of other pollutants, 2-ethylhexanol, an airway irritant, and benzene, which is harmful at any detectable concentration. Passive sampling exposure was over 4 days, including unoccupied hours in the evening and at night, in 1 week in winter and 1 week in summer. The winter season in this study includes months from October to April and the summer season includes months from May to September. The passive samplers were mounted on the wall at approximately head height, so out of reach of children. Here are the VOC samplers, and in the second image, the multi-sensor unit used for logging the continuously monitored parameters, while temperature and relative humidity outdoor were monitored using a different unit in an appropriate enclosure. The two case study schools are primary schools, Passive House certified, and in the UK. School A is located in the West Midlands in a suburban setting, and School B in an urban location in London. School A is a two-form entry school, and School B is an extension to an existing school for its expansion from 2 to 3 form entry. Both schools are mechanically ventilated in winter and have mixed mode ventilation in summer, but have different ventilation control strategies. School A has CO2 controlled ventilation rates with a set point at 1500 ppm, and School B has fixed ventilation rates at 8 liters per second per person in its classroom. Both schools underwent soft landings and interventions for fine-tuning, which ended in 2015 and 2017 respectively. So current settings correspond to different versions of the guideline, the 2006 and 2018 Building Bulletin 101. 3 classrooms were surveyed in School A, 1 on the ground floor and 2 on the first floor. One of the classrooms was north-facing and the other 2 were south-facing. The surveyed classrooms in School B were all on the first floor, and again 2 were south-facing and 1 classroom was north-facing. The table summarizes the classroom characteristics across both schools. The classrooms have similar occupancy density, 30 to 32 children in each classroom, and similar floor areas. Classroom volumes in School A were a bit more varied. School B classrooms have high-level south-facing windows, whereas School A classrooms don't. Window design has more airflow obstruction issues in School B. It is also noted that some variation in window design exists within each school. School A ground floor classroom has a door which leads to the playground, therefore increasing significantly the achievable airflow rate through natural ventilation. And School B, north-facing classroom B4, did not have the grilled safety vent seen here in the second elevation. On the next slide, these pictures show a classroom in School A and a classroom in School B, featuring different types of carpet flooring. Small areas in its classroom, the area around the sink, are non-carpet flooring like linoleum or rubber. Moving on to the results. The graph on the slide shows the distribution of temperatures in winter and summer in the classrooms and 1 outdoor location for each school. The summertime overheating risk assessment showed that there was no overheating risk in summer according to adaptive criteria for the monitored period. The percentages on the graph show exceedance of upper and lower limits for winter thermal comfort. A higher tendency for winter overheating can be observed in 1 classroom, B4, which is the north-facing classroom in School B. Milder tendency for overheating can be observed in the other School B classrooms and the first floor south-facing classroom in School A. These classrooms have unshaded glazing areas facing south. Relative humidity levels were generally within the acceptable range, but with narrower ranges observed in School B. The graph shows classroom CO2 concentrations in each season. The horizontal lines mark the average concentration limits corresponding to the 2006 guidelines at 1500 ppm and the 2018 guidelines at 1000 ppm for mechanically ventilated buildings. In addition, according to the current guidelines, the 1500 ppm limit should not be exceeded for more than 20 consecutive minutes. It can be observed that during the heating season, classroom CO2 levels were higher in School A than in School B, and that averages in School A were below the 2000 limit, while averages in School B were below the stricter 2018 limit. On the same graph, these horizontal dashed lines now represent the average CO2 levels reported in literature for UK schools, primarily naturally ventilated in summer and in winter. We can observe that on average, winter CO2 levels in these passive house classrooms were well below those previously reported. And the last graph on CO2 concentrations shows the maximum daily average in its classroom, the limits that we mentioned before, and the number of days that these were exceeded. School A only meets the 2006 requirements, while School B meets the current requirements as well. According to UK building regulations, acceptable indoor concentrations of total volatile organic compounds are below 300 micrograms per cubic meter. In both schools, the measured levels were below this limit. The highest concentrations were in School A in winter. Thus, higher ventilation rates in School B do seem to limit indoor concentrations of total volatile organic compounds. And this graph shows limonene concentration levels. Again, the highest concentrations were recorded in winter in School A classrooms. The variation within School A could be explained by the loading factor of non-carpeted floor area, that is, flooring area, which is cleaned with a wet mop on a daily basis, divided by the room volume. Therefore, we can expect higher concentrations with heavier use of cleaning products. Another compound is 2-ethylhexanol, and it was only found in School A. This is associated with recent repainting. Benzene levels were low, close to detection limits. Nitrogen dioxide, NO2, has no indoor sources in UK schools, and studies found that indoor nitrogen dioxide in classrooms follows outdoor concentrations of the pollutant. This graph shows the average indoor nitrogen dioxide concentrations in each season and school, while the outdoor concentrations are shown with the dotted lines. Outdoor nitrogen dioxide is lower in summer than in winter, but indoor to outdoor concentration ratios are higher in summer, therefore leading to similar indoor levels across the seasons. The fact that School A in winter has lower indoor to outdoor concentration ratios compared to School B could indicate that increased ventilation rates also increase infiltration of nitrogen dioxide into the classroom. There is no indication that air tightness may limit infiltration of the pollutant to indoor air in school. Existing literature offers contradicting evidence on this. In this graph, we're looking at PM2.5 concentrations in indoor and outdoor air. Indoor concentration levels are below the World Health Organization limit for long-term exposure. Median indoor to outdoor concentration ratios were lower in winter than in summer, and lower than those reported for naturally ventilated schools, suggesting lower infiltration of the pollutant in mechanically ventilated schools due to filters. This is, however, not conclusive, as some studies showed that indoor particulate matter, PM2.5, can have different chemical composition indoors and suggesting considerable indoor sources. The next slides will summarize some key findings and their practical implications for school design and operation. Based on temperature monitoring, all classrooms met the criteria for summertime overheating risk, but there was a tendency for overheating in winter. Also, higher temperatures were observed in classrooms with increased solar heat gain. This must be carefully considered when designing external shading, especially for the high-level windows. Both ventilation and control strategies were successful in meeting the criteria that they were designed to in terms of CO2 concentrations. The monitoring showed that at a fixed rate of 8 liters per second per person, winter CO2 concentrations were similar to summer levels. This was not the case in passive house classrooms with lower ventilation rates in School A, but the seasonal difference was not as pronounced as that reported for naturally ventilated schools in the UK. Existing literature offers contradicting evidence on how building characteristics and operation may influence indoor concentrations of nitrogen dioxide in schools. This monitoring suggests that higher ventilation rates can increase the infiltration of the pollutant into the classrooms, while airtightness does not seem to be a factor. Continuous monitoring profiles would be useful for investigating further the building's ability to protect occupants from outdoor-sourced nitrogen dioxide. Higher ventilation rates did not increase classroom PM2.5. As fine particulate matter is considered to be mainly outdoor-sourced, this could be an indication that in a mechanically ventilated, airtight passive house school, filtering can protect the occupants from this pollutant. Monitoring of targeted VOCs, in particular limonene and 2-ethylhexanol, suggested that there is a need for schools to tailor ventilation schedules to the cleaning schedule on a daily basis, and to increase ventilation rates for several months following any repainting of the interior. Our next steps in this ongoing research project will include to report findings on more monitored parameters, the coarse fraction of particulate matter, other important VOCs and aldehydes, such as formaldehyde, and also to determine which factors influence thermal conditions and indoor air pollution in passive house classrooms, and how do these compare to other school buildings in the UK. So this is the end of my presentation. Thank you for listening.